Why?
A striker breaks the defensive line. A center back slides in. The crowd roars. The ball deflects, the whistle blows, and a penalty is awarded. It all happens in the space of a single heartbeat. At the apex of that decision, the human eye is forced to track 22 moving bodies and a ball, evaluating contact, intent, and physics. Elite players sprint at 30 kilometers per hour. The ball routinely travels at 130 kilometers per hour. Yet the human brain requires roughly 250 milliseconds just to register a visual stimulus and react. By the time a referee processes a tackle, the ball has already moved nearly 9 meters. The physical speed of modern football has outpaced the biological hardware we rely on to officiate. This biological bottleneck has dictated the outcomes of World Cups. Frank Lampard's shot crossing the line against Germany in 2010, or Diego Maradona's hand of God, are direct results of relying on a single pair of eyes in a massive, fast-moving space. A single missed frame in a referee's vision cascades into profound frustration for millions watching. In sport, the margin of error carries massive emotional weight. In the 1990s, analysts attempted to log these events manually. They sat with clipboards or early computer databases, trying to record the match data by hand as the game unfolded. Video assistant referees were introduced to catch what the on-field official missed. However, the system requires human operators to parse multiple camera angles and overlapping two-dimensional feeds under intense, severe time pressure. Even with the aid of technology, the referee must still walk to a pitch-side monitor. The final decision ultimately remains bottlenecked by the exact same human perception that missed the call in the first place. Adding more cameras to the stadium did not solve the delay in processing time. The sport required a non-human brain. To an AI, a live video feed is a raw mathematical problem. Using convolutional neural networks, or CNNs, the system sweeps across the video frame, stripping the image into a massive matrix of pixel values. Vision transformers fracture the pitch into a grid, treating each patch as a data sequence. Attention blocks draw mathematical connections, evaluating relevant patches instantly. Finally, it maps 3D pose estimations over players, tracking skeletal joints and velocity 50 times a second. Through this process, the physical chaos of the match transforms into a perfectly measurable digital matrix. Extracting this data requires massive computational scale. Modern systems track over 3,400 distinct events per match, alongside continuous location data for every player. This data allows for the calculation of expected goals, or XG. By cross-referencing a shot against millions of historical data points, the system determines the exact statistical probability of that action resulting in a goal. Elite managers rely on this intelligence layer to design pressing tactics and assess player value. A coach's observation is now paired with spatial evidence. By formalizing the patterns of the match, these models provide a framework for decision-making that turns once intangible movements into measurable probabilities. However, deep learning models operate as black boxes. When the AI makes a determination on an offside call, the exact mathematical path it took to reach that conclusion is often invisible to the engineers who built the system. Computer vision can also suffer from algorithmic hallucinations. During a match, the model might mistakenly draw a red bounding box around a stadium shadow or a cameraman, misclassifying them as an active player. This precision raises a philosophical question. Football culture is built on the shared experience of human drama and the tension of debate. Removing error risk also risks removing the emotional friction that fuels the sport. While AI provides incredible accuracy, that perfection can sanitize the volatility that makes the game a global obsession. The technology is moving beyond passive tracking. The trajectory points toward fully automated officiating and generative AI models that can design playbooks based on an opponent's real-time weaknesses. This digital reconstruction illustrates the growing complexity of the sporting environment. It highlights how the physical stadium is layered with predictive algorithms. A machine learning intelligence layer now sits between the camera and the viewer, interpreting every player's movement in real time before the signal even reaches a screen. The next time a striker breaks the line to score, the machine will know the outcome before the human eye even registers the movement.